The third part of the GPS system is the end user segment. This is the part that we're most concerned with because it's the part we interact with as we're trying to actually use the GPS system to be able to calculate our position. So what does the end user segment determine? It's really based around our receiver. And our receiver, we use that to collect information, to decode that information is being broadcast by the satellites, and process information in such a way that we can calculate the position. The big thing about a normal receiver, GPS receiver, is that it is a receiver only. It does not have a transmitter, so we're not actually communicating with the satellites directly or broadcasting anything to the satellites. It's a receive only type of system. Very similar to if you have a TV and you plug an antenna in the back of the TV to receive TV broadcast. It's a very similar thing. You're not transmitting anything back to the TV station. You're receiving that signal, decoding it, and presenting it on your TV. So the process here is that the receiver needs to determine its location using these signals that are being broadcast by each of the satellites. And the method we do that is what is known as trilateration. Now in GPS, trilateration, as the term means, tri means three. Lateration, we're talking about lateral, so we're talking about distances. So we need at least three distances to be able to determine a unknown point. And the three distances we're going to be using are distances from our receiver to the satellites themselves. Now, every single satellite, as we've talked about with the control segment, is orbiting the Earth and maintaining a particular altitude above the Earth's surface. So it's at some known distance from the center of the Earth, and we can collect the information, our distance, and calculate our distance to that satellite, but that doesn't really help us much at all because we need more than one to be able to calculate our true position. And the reason for that is because if we think about a single distance, there are multiple points that we could actually have that distance away from the satellite. And if we're talking about something in three-dimensional space, a single point in three-dimensional space, a single distance between 2 points, is going to generate a sphere. In the case of satellite GPS distances, when we calculate distance to our receiver, we know we're on the surface of the Earth, so we can eliminate a lot of points. And so essentially we're going to have a single distance to a single satellite is going to create sort of a round or an oval shape on the surface of the Earth, depending on the terrain that we're looking at. So essentially there's an equal distance line from our receiver to the satellite, and that can be a lot of different places on the Earth. So we need another satellite to be able to help us out. So if we take a second satellite and we calculate the distance to it, then that creates two circular shapes, and two circular shapes are going to overlap. And at worst case scenario here, we're going to have 2 points in which we have the exact same distance from both satellites. Best case, we hit a point where both of our circles are tangent to one another and we only need 2 satellites. But that's usually not going to be the case, so we need to have an additional third satellite to have that distinct trilateration, or that distance between 3 points, to lock in, create no other possibilities or combinations in which we can have that. Now, this works great in a perfect world. Unfortunately, we're not going to be able to calculate our distance to each of these 3 satellites super precisely, and so there's going to be some error in that system that's just inherent there, and so we have to have additional satellites to help solidify and resolve some of that error. And how do we calculate the distance? Well, we basically are looking at calculating distance to each of those satellites, and there's really 2 types of ways in which we can calculate that. We talk about ranging, and ranging is just basically calculating a distance between 2 points using some type of signal. And the 2 types of ranging that we're going to talk about are code phase ranging and carrier phase ranging. And the first one's going to be using the code, the second's going to be using the carrier wave. So for code phase ranging, we've already kind of discussed this a little bit, and that every satellite has this pseudo-random noise or this PRN signal that's unique to each satellite. It's transmitted, it's roughly 1,000 bytes of data that's continually being repeated on that CA, L1 CA signal band. When the satellite starts that and ends that, it's going to be unique to that particular satellite. And so your receiver knows that whenever it sees a signal, like for example here at the bottom of the page in blue, if that's the sent signal, it receives that signal, it knows exactly that that's from satellite number 3, for example. And so it's going to have internally its own database of what every single PRN code should look like for a particular satellite number 1 through 27. It's going to then receive a signal from a particular satellite that it's locking onto, and it receives that signal. And based off of that signal, it knows that the pattern of that PRN is satellite number 3 in its database, but as it's replaying that signal in its database, it knows that signal is supposed to start, let's say, at 12 noon is when one of the signal cycles begins. Well, when it receives a signal, it's not at 12 noon, it's not matching up correctly. It lays them over top of each other with when it's received, what it should be reading at that particular point in time. And so it knows there's going to be an offset here. And so what your receiver does is going to basically try to shift the received signal to match its signal that it has in its database to make sure that the two are the exact same PRNs. And so we shift that sent signal back till they match correctly, and then that amount of shifting that we do, that's going to be our phase shift or our time offset shift. And that time offset is going to be what we're going to be using to actually calculate the range or the distance. And the way we calculate that is just using a simple rearrangement of velocity equation. We know velocity is distance divided by time, and to calculate distance, which is our unknown, we need to have time and velocity. Time, something we just calculated, or I showed you how your receiver is calculating by finding that phase shift distance or that time offset between the signal that's received and the signal that's replaying in its own database. And velocity is simply the speed of light, because all of our radio waves are going to follow that speed of light. And so since we know the velocity and we know the time offset, we can then calculate the distance between the sender being our satellite and the receiver being our actual GPS receiver. So for example, if we're going to be calculating a code phase range distance, if we want to look at the distance between the receiver and satellite, and say our receiver calculates that the signals were offset by 0.23 seconds, we know that the speed of light is roughly 186,000 miles per second, or right at 300 million meters per second. And so we just plug that into our distance velocity equation. And so 186,000 miles per second, converting that to feet with 5,280 feet per mile, times the number of seconds that our receiver calculated, 0.23, we get just around 226 million feet distance between the receiver and the satellite. Now that works great for many different cases, but carrier phase ranging is something we see that was originally very popular, especially in surveying types of receivers, because we need a lot more precision. But we're seeing this in a lot of things nowadays. A lot of our receivers can utilize carrier phase ranging. And why do we even use carrier phase? Well, just to set up the reason for not just maintaining that code phase versus using carrier phase. If we look at our two signals, we have our message signal, which would be that 0 and 1, and then we have our carrier signal, which we know to modulate the carrier signals we talked about in the space segment, we are using a much lower frequency message signal compared to our carrier signal. So our message signal for the L1 course acquisition signal that we've been talking about, it's at 1.023 megabits per second. So we can say roughly 1 megahertz is the bit rate for that particular message. So we get a bit every 1 microsecond. If we use the speed of light, that means that each bit is taking up a 300 meter wavelength. So the wavelength between each of those is going to be 300 meters long. Now, what does that mean? That means that if we're matching up and sliding that carrier wave over from the receive versus what we have internally, if we're off by a little bit, then we're going to be somewhere in that 300 meter range. So as long as we're not off by a bit, as long as our bits are lining up, we're going to be only at maximum off by 300 meters, which is still a huge amount of distance for a distance from a satellite. If we look at the carrier signal, it's operating at a much higher frequency at 1575.42 megahertz. That's a cycle or a rotation here, cycle every 0.63 nanoseconds. And so if we use the speed of light calculation that to find the length it takes for one cycle, we get about 19 centimeters is our wavelength. And so that means that if we were trying to use the carrier signal as our pseudo-ranging background here, then if we, long as we were within basically one cycle, we could only be off by 19 centimeters difference. Now, why does this matter? Well, there's kind of this rule of thumb estimation we call the 1% rule of thumb, and it says that basically for any type of pseudo-ranging process, the max achievable resolution that we can get is 1% of whatever the signal bit rate is. So for example, for our normal L1 course acquisition rate that's 1 megahertz, that gives us that 300 meter wavelength, that 1% would mean that the most precise we could actually get with that signal alone would be 3 meters resolution, which is about right for an autonomous GPS signal. Using the carrier signal, if we think about it, it has a 19 centimeter wavelength. It's at a much higher frequency, so we're going to be able to have an max achievable resolution of around 2 millimeters, which is tremendously different amount of resolution here. But there are some issues with using the carrier signal. One of the big issues is if we look at the carrier signal, my message signal here is a very nice, consistent kind of sine wave, but we know that our PRN code is not a sine wave. It is a random noise sine code, so we can actually find the exact point in the full length of the message that we're at by shifting our code. With the carrier signal, we have nice, consistent sine cycles. The cycles are the same, and so it makes it difficult to figure out where we are, the number of whole cycles. And so a lot of high accuracy receivers use this carrier phase ranging. But if we think about a GPS satellite sending a signal out to our receiver, we've got a number of cycles that we need to determine to be able to find the length. We're going to call that rho. And then we have a partial cycle. We know that there's going to be some partial piece of a whole cycle that we're going to have to finish out that last little length. And that partial wavelength is what we call phase ambiguity, which is essentially determining and making sure we're kind of calculating that difference. So whether we're out of phase by 90 degrees or 180 degrees, so basically a quarter wave or a half wave length, that's that piece that we have to be able to maintain and our receiver be able to adjust for that. And then there's the whole number wavelengths, or that rho, and that's the one that's really difficult with carrier phase ranging, because it's difficult with a single one-way ranging. We're not transmitting a signal there and receiving that signal back, and so it makes it difficult to actually count or determine the whole number of wavelengths there. And so We call that the cycle ambiguity or the integer ambiguity, and that's the one that's difficult. The nice thing about that is there are a lot of methods out there to help us try to determine that. And as long as we're locked onto a satellite and we're constantly receiving a signal from it, the nice thing is that length is going to be typically consistent. And so that'll help us a lot to be able to calculate this. But carrier phase ranging is something that we do. And one of the other ways that we can actually calculate that or help us to calculate that is we use our code phase as a way to get us close. And then we use carrier phase as a way to kind of narrow us down. So if we know that the full length is, something really close and we're just off by a little bit, then that partial wavelength is what's going to help us out here with the carrier phase ranging.